the audience that is here for this moment is mainly to ask interesting questions, and it'll be the wider dissemination that really makes an impact. This is one it's a pleasure for me to introduce because I've seen Robert and Caccione grow over the last few years, and it heralds a really interesting approach. I know that we're going to talk about batteries and the construction of batteries, and Skyler and doing all the sort of techie stuff. But what really grabbed my attention in the first place with Robert's work was his engagement with the people, actually listening to the people and spinning off from women's groups and creating the solar shops, etc. I believe he's expanded to 20 shops now in various areas. So, Pete, can you just mute, please? Sorry, I can hear you shuffle every now and then. Right, so let me introduce our two speakers today, Robert Van Buskirk, who seems to commute between California and Malawi, and Skyler. I don't actually know where Skyler lives, so I'm assuming he's an American, and we'll see. He may chastise me and say, no, I'm Canadian.
Yeah, San Francisco. Yeah.
Okay, so Robert, would you like to make a better introduction to the whole setting and program?
Yeah. Skyler's a electrical engineering PhD student at Stanford University, which I was trying, we in Caccione were trying to solve the battery problem, and the problem with batteries is that they die very quickly, especially if you cycle them often, as you might do with a cooking system. So Skyler began doing cycling tests for various batteries we were sourcing. And we realized that if we really wanted the battery to last 10 years, we had to move to lithium titanate technology. So Skyler's traveled to Malawi twice. He's visited the villagers. He's seen them use lead acid batteries, which die in 6 months. And he saw very concretely the problem that needed to be solved. And he's iterated on that problem several times until now we have a battery that works well, and which is customized to solving the cooking, the energy regulation problem for cooking in rural villages in Malawi. So that a good enough intro, Skyler?
Yeah, that's
So why don't we move on to the presentation? Skyler, can you present? Okay, so we're going to talk about making a 10-year lifetime solar eCooking battery for rural Africa, where we customize lithium titanate technology, lithium titanate chemistry for application to low-income households that are doing off-grid solar electric cooking. Next slide. And a key thing is to know what the parameters of the cooking process are. So we've been working with people for 5 years on cooking issues, and we've recently conducted some surveys that got the cooking details very well specified. In addition, we've done cooking tests where people have cooked thousands of dishes. So with the cooking of thousands of dishes, we've been able to get some good statistics on the energy use. With the surveys, we've been able to see what people cook. So typically a household in rural Malawi cooks an average of about 5 dishes per day. 2 of those dishes are nsima or ugali. It's known as ugali in Tanzania, Uganda, Kenya. Another dish is a root starch, either sweet potatoes, Irish potatoes, or cassava. Then a vegetable, which typically is greens. And then a protein, which is fish, soybeans, or meat, or regular beans or meat. The cooking energy intensity is between about 150 to 350 watt hours per kilogram of food cooked. People eat roughly 2,000 calories per day, and on average, the cooked food has a caloric content of about 1 calorie per gram or 1,000 calories per kilogram. That means people in rural Malawi eat an average of about 2 kilograms of cooked food per day. This means for a household of 5, they'll be eating about 10 kilograms of cooked food per day. And if we take the average energy intensity of 250 watt hours per kilogram, that means the cooking requirement for a typical household in rural Malawi is about 2.5 kilowatt hours per day. Currently, we distribute a 700 watt peak battery-free off-grid solar e-cooking system, and we're finding that people do about 1 kilowatt hour of cooking on that system each day. So to get up to the full household cooking requirement will require either battery that stores energy and uses the solar panel electricity more efficiently, or larger solar panels. Next slide. This is our battery-free system. The bulk procurement cost of a battery-free system is about $160. That's largely because the price of solar panels has dropped so far. Right now, we can get 72 cell solar panels that are greater than around 350 watts for about $50 each. When we buy them by the container load, we can get a maximum PowerPoint tracking controller that can regulate 600 watts of power for about $30 each. And these direct current insulated electric pressure cooker has a bulk procurement cost of about $30 each, not including import taxes. So hopefully we'll get a tax exemption to keep it at $30 each. So that's the bulk procurement cost. And what happens is if you have a battery, you add the battery between the maximum PowerPoint tracking controller and the cooker, and the battery regulates the electricity that's going to the cooker and uses that electricity more efficiently. So let's go to the next slide. This is an example of what happens when the battery is sitting between the solar panel and the cooker. In this particular case, the solar panel is only a 350 watt solar panel. And we have 2 plots here. The upper plot has 2 traces. The red trace is the power that is going from the battery to the cooker. The green trace is the power that's going from the solar panel to the battery. And, you know, the difference between those 2 traces results in a discharge and charging of the battery. The battery voltage is the bottom blue trace, where you see early in the morning when they turn the cooker on, the battery discharges. Once the battery is discharged, the power that goes to the cooker is pretty well matched to the power coming from the solar panel. Then once that first dish is cooked and the cooker is turned off, the battery keeps taking energy from the solar panel and it charges up. And then you wait between that first dish and now the next dish around lunchtime. And around lunchtime, you can see the power coming from the solar panel and the battery adding some extra power. And because the battery adds extra power, that lunchtime dish is cooked faster, and that saves people time, and people appreciate that. So then at around 2 o'clock in the afternoon, that dish is finished. The solar panel keeps charging the battery until the battery is full. And then at the end of the day, the battery has a little bit of energy available for cooking that last dish right there. So what 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 is happening is any time the power isn't coming from the solar panel, that is power that is not used. So we do want the bigger and bigger, the bigger you can make the battery, or the more frequent you can make the cooking of the dishes, then that means more of the electricity from the solar panel winds up being used. So let's go to the next slide. So in this slide, we have the statistics of, these are cooking tests in one of our women's shops. And we find that there's a correlation. So if you have a cooking station, and what happens is these are battery-free cooking stations. So the amount of energy available varies from day to day. And on the days where they have more energy, they cook more dishes. So it's sort of scientifically nice to have the variable availability of energy, because with the variable availability of energy, we get to see how the number of dishes they cook changes, and how the energy per dish changes. So so in this particular slide, you see that, you know, when a system is providing on average about 1 kilowatt hour per day, then that system will likely be cooking about 2 to 3 dishes. And what we have is, when the battery is small, essentially the battery is going to cycle every dish. And so if a household really wants to cook 5 dishes of food per day, that battery is going to cycle basically 5 times per day. So on to the next slide. So what happens is, you know, here is a case of looking at the economics of 3 different battery chemistries, and the idea is to amortize the cost of the battery over the kilowatt hours that the battery delivers. And so what happens is, to estimate the per kilowatt hour cost, you estimate what the annualized cost of the battery investment is, and then you divide by the kilowatt hours per year that the battery is delivering. And the annualized cost of the battery investment is given by a factor which is called the capital recovery factor. So the annualized battery cost is the total battery investment times the capital recovery factor. And the capital recovery factor is given by the equation in this slide, where I is the interest rate and N is the number of years over which that the battery is operating. So when you do this calculation with different costs for different battery chemistries, so here we estimate from surveying the market in Malawi that the lead acid batteries are running at about 20 cents per watt hour. We'll see later in the talk that our LTO battery is about 80 cents per watt hour, and we're roughly guessing that the lithium iron phosphate battery would be about 40 cents per watt hour. We don't really know, because the lithium iron phosphate isn't being distributed in Malawi very much, so it's hard to find lithium iron phosphate batteries being sold. But we see that when you're cycling the batteries 3 times per day, the lead acid battery is only going to last about 6 months, a little over 6 months. The lithium iron phosphate battery, if you're cycling 2.5 times per day, is going to last about 3 years, whereas the lithium titanate, the LTO battery chemistry, should last 10 years. And because of the long lifetime of the LTO, you're amortizing the cost over many more kilowatt hours, and the per kilowatt hour cost of the electricity being managed by that LTO battery is now down to only 10 cents per kilowatt hour. So so that's the goal, right? Current lead acid, if you use it for cooking applications, that's going to cost you 41 cents per kilowatt hour. Lithium iron phosphate gets you closer. It's about 14 cents per kilowatt hour, but you're going to have to maybe replace it in 3 or 4 years. And the nice thing is with LTO, it can hopefully last 10 years, and the per kilowatt hour cost drops down to 10 cents. So that really is the economic reason why we're pushing for the LTOs. So I think that's next slide. Oh, right. And then here's the slide that shows the per watt hour cost of the battery cells when you buy them from the factory door in China. What happens is the per watt hour cost of the lithium iron phosphate is about 12 cents per watt hour. The per watt hour cost of the lithium titanate is running at about 20 cents per watt hour. So the difference between the lithium titanate and the lithium iron phosphate is running at about 8 cents per watt hour right now, which means if you have other costs to constructing or building the battery, and you really can build either a lithium titanate or a lithium iron phosphate, then you know because there are so many other costs to building the battery, the extra cost of the lithium titanate isn't necessarily that big, right? It's about 8 cents per watt hour. Okay, so I think at this point I'm gonna hand it over to Skyler for explaining how we actually build a lithium titanate battery.
Okay. You are on mute, Skyler.
Is that better?
That's better. Yeah. Okay. Thank you.
All right. Thanks for letting me know. So yeah. So let's talk about how we can make an actual battery system from these cells, and we'll talk about how it's generally done in the industry, and how we can modify that process to minimize costs and make a custom system that will work for a home cooking system in Africa.
Sorry, again, you're on mute, Skyler. You must have accidentally touched it, so.
Okay, yeah, I think I was it clicked or something. Okay.
That's all good. Thank you.
Hopefully it'll stay. Okay. So yeah, let's talk about how batteries work in general, and we can describe just the most common lithium-ion battery, which is called the LFP battery, or lithium iron phosphate battery. And basically all batteries kind of work the same way. So you start with the two materials, and these two materials, they have chemistry such that when you touch them together, they'll react. They'll react quite violently and release a lot of energy. And the way that they'll react, for example, in this case, is that lithium ions and electrons will go from one material to the other. And you know, in this case, unless you're trying to make you know, a fire or a bomb or something, it's not so useful. You would want to kind of extract half of the reaction out. You want to get the electrons without the lithium ions and send that through some sort of load device, some electronic device like a phone or a cooker that you might have. So in order to do that, you can kind of provide two routes. You can have a route where the ions can go through, called the electrolyte, and the electrons can't go through it. It's not conductive. And then a route the electrons can go through, which is just a wire or a conductor, like a metal. And the ions can't go through that. And so when you put those things in your system here and you connect them to these two materials, you have a battery, and you can kind of see how the electrons will go through your load and the lithium ions will go through this electrolyte. Okay, and you can kind of you can see here the different reactions happening at the anode and the cathode. So the anode is the negative terminal for the battery, and the cathode is the positive terminal. And generally, the battery is referred to by the cathode material. In this case, when it gets discharged, it's a lithium iron phosphate. But you can have many different cathode materials. You can have lithium cobalt oxide, lithium nickel manganese cobalt oxide, lithium manganese oxide, lithium iron phosphate, lithium nickel cobalt aluminum oxide, and there's even more than this. But when we're talking about LTO batteries, well, we'll see all of these batteries in general, they'll have the same anode material. Basically, any battery that you'll find in your car or in your electronic devices at home will have a graphite or just a carbon negative anode material. But there is another material you can make the anode out of, and that is lithium titanate or LTO. So when we're talking about these LTO batteries, we're actually talking about the anode material. And because you're now customizing the anode material, you get a whole bunch of different properties for the battery. And it's a completely different lithium ion battery. But also because carbon or graphite, which is just the material you find in your pencil, is extremely cheap, you can make batteries with graphite anodes for cheaper. Introducing lithium titanate into the anode increases the cost of the battery, and it also decreases the voltage of the battery. So this kind of lends to the major cons of any LTO battery, and that's they will be more expensive because lithium titanate is more expensive than graphite, and they will be less energy dense because of the reduced voltage. So normal lithium ion voltages with a graphite anode will have around 4 volts terminal voltage. And when you introduce LTO, it reduces the electrochemical potential between the two materials, and the voltage of the battery will be reduced to around 2 volts. On that, therefore reduces the energy density of the battery somewhere by around a factor of 2. And these cons for most consumer electronics are, serious issues, right? You kind of want as much energy and as small package as possible for, of course, as cheap as possible. But for our home cooker design, we have kind of different requirements. So if you look at the pros of an LTO battery, things that it is especially good at, is that they last an extremely long amount of time. And that's for a few reasons, but the major reason is because when the lithium ions come in and out of the carbon material, of the graphite material in the anode, it changes the volume of the material. So the material is constantly expanding and contracting, and this causes physical strain, cracking, and just degradation of the material over long periods of time. But lithium titanate, it's kind of they call it a zero strain material. As the lithium ions come in and out, it doesn't change volume nearly as much, lending to longer lasting batteries, sometimes in excess of 10,000 cycles. And further, the lithium ion kinetics, how they move around in this kind of chemistry here, they're much faster to move in lithium titanate than in graphite. So this allows them to, allows the battery to emit more power and have a lower internal resistance. And so, this particular advantage of having a higher power capacity has seen some applications of LTO batteries in electric cars because you need a large power output by the battery. But these two advantages are kind of well suited for our system, right? Our major requirements is that it has to last many cycles over many years. And also cookers are, you're cooking at a very high energy for a very small amount of time. So the power capacity is also very important to us. So this kind of shows that, the design requirements of our system is really met very well by the LTO lithium ion chemistry. Okay, so yeah, we don't care too much about the space that these things take up. So it makes one of these the major cons that are normally associated with LTO batteries not really matter for us. But we of course still need to address the cost of LTO batteries, right? And you're going to be cost limited in any sort of engineering instance, especially when you're designing for, very, very cheap end products. Okay, so we'll talk a little bit about here how to generally make a battery system. So starting with the cells, you need to first protect the cells from the environment, and this is generally done by having just a box or a case around the cells, and also having a kind of a watertight encapsulant, just putting glue around the entire array of cells here to prevent them from water getting in there, and to help protect them from shock if you drop the battery or something like that. And then you also need electrical protection. And we'll talk a little bit more about this in a second, but this is generally referred to as the battery management system, which is just a circuit board that monitors the voltage of each one of the cells in your battery stack and performs certain operations on the cells, allowing them to not be damaged by electrical loads or charging that you apply to the battery stack. So also it's good to mention here that the voltage that you get from a particular lithium ion cell, in the case of LTO, 2 volts around, is usually not good enough for any applications, right? So in order to get a reasonable voltage, say 12 volts, which is the same voltage as like a car battery and the voltage that we're designing for, you need to cascade. You need to just stack multiple of these cells on top of each other to get the higher voltage. So you generally have a minimum of 5 cells in a 12-volt battery system. And you also need a thermal protection. So the battery cells will be damaged if they are overheated, either by some of the electronics or maybe the environment, the sun shining on it in any case. This can be done by adding heat sinks to the electronics and also using thermally conductive encapsulants, basically epoxies or silicones that are impregnated with different kind of thermally conductive materials that are not electrically conductive. And finally, you have to combine all of these elements together. Usually the electronics are done by a machine called a pick and place machine, where the assembly of the circuit boards is very streamlined, and it's a common industrial process and can be done for very cheap. And the assembly of the entire system, the encapsulating in the box and connecting it to the electronics, connecting the cells together, it's usually done by hand for batteries at this size and scale. Some car batteries, I think they will have robotic arms and they'll have more automated assembly, but as far as I can tell, that most of these kind of consumer or desktop size batteries will be done mostly by hand. Okay, so let's talk a little bit more about the electrical protection, the battery management system. So this has to protect from multiple different sources of damage. So if the lithium titanate cells are under voltage, if the voltage on their terminals ever drops below 2 volts, they will be damaged. And the same thing will happen, or they'll also be damaged if they're over voltage. So the voltage on the cells has to always stay between 2 and around 2.7 volts, else unwanted chemical reactions will happen in the materials that are not reversible and therefore degrading the battery. Also, the cells in the stack, so that our 5 cells in the 12-volt battery have to be balanced, else you get problems with the cells kind of working against each other. And the battery management system should also protect against over temperature, as discussed before, basically shut off the charging or the load if the temperature reaches a certain threshold. And if you accidentally short circuit the battery, which can happen, either by setting it up improperly or some water getting onto the terminals, say if you have a leaking roof, and the battery is kind of sitting in an area where the roof is leaking onto, you might get a short circuit. So the BMS should have some protection on that as well. And this is normally accomplished electronically where here this big box is just representing our whole battery. And here I'm only showing 2 cells, but you can have as many as you want in this case. But this is just 2 cells for demonstration. This battery management is in general conducted by a single chip, or sometimes it's conducted by just a single integrated circuit, right? In the cheapest case here, where this integrated circuit basically looks at each of the voltages on each of the cells, and can even sync current out of individual cells, allowing them to balance and reach the same voltage. And it'll also sense the current into and out of the entire path through a sense resistor, and control an electrical switch here, switching it on and off depending on whether the cells are under voltage, over voltage, or too much current, or something like that. And these integrated circuits are generally very cheap, usually less than $1, and they can control the entire battery stack. The other way of doing it, the more sophisticated, but kind of the gold standard in terms of BMS systems, is to have this kind of 3-chip solution, where you have some analog front end, which is doing all of the voltage readings and the high voltage switching that is needed for this switch. That's all controlled by some analog circuitry in one integrated circuit. And that talks to a microcontroller, or a little computer, basically, that will program the analog front end and tell it what exactly to do. And you can even have this extra chip here called a fuel gauge, which will contain some algorithms and some processing capabilities that will allow easy computation of the total, the life of the battery, like the degradation over many years, and the current capacity of the cells, and have some of that those algorithms already baked into this fuel gauge. So having this computer in there also allows us to output data to a memory card, and this is important for our case, because we want to log how the batteries are being used. Like Robert showed a plot earlier of the current into and out of the battery that was obtained by such kind of memory card logging. And it also allows us to show that the batteries are being used and allow them to be subsidized. So another thing is that this cheaper solution here doesn't really exist for LTOs. As far as I can tell, there are no companies that make integrated circuits that fit the voltages of LTO cells. These chips are not programmable after the fact by the microcontroller, like in the case on the right side here. And that means you have to buy them conforming to a specific cell voltage. And nobody makes single chips, or nobody makes ICs that conform to the LTO cell voltage. So we have to use this system on the right, this triple chip system, and which is generally more expensive. But we'll talk about how we can minimize the cost of our electronics. Okay, so we'll talk about minimizing the cost of the physical protection. So the way we've done that in our battery is to take basically the encapsulant and have that be the only and physical protection. And the encapsulant can be made out of engineering materials like epoxy. It can be very stiff and can be sufficient to protect the battery on its own. So you can see here we've made kind of a removable silicone mold that we make the entire battery in. We pour the cells and the electronics. We pour an encapsulant on it that is a stiff epoxy, and we can then remove the reusable mold. And we don't have to buy this outer case, depending on your case. That could be around $3 to $8, depending on how thick your box is. And for the electrical protection, we talked about this 3-chip solution. In reality, with some careful design, we can absorb all the functionalities of the analog front end and the fuel gauge into the microcontroller itself. And this can save us from $2 to $8. For thermal protection, we'll do away with heat sinks, and we can just use minimally. We can use thermally conductive encapsulants and just a minimal use of it right over the areas of the battery that get hot, which are the switches, in this case, the high power electronic switches that control the current into and out of the battery. And you can see the clear epoxy in this case is the cheap epoxy that is over most of the battery. And the black here is this thermally conductive epoxy that's impregnated with thermally conductive material. And that's only over a very small area. Another advantage of these LTOs that we've talked about is that they have high power capacity, right? So we don't have to worry about them heating up when we're using them at high currents, which is also an issue with other types of lithium-ion batteries. But in our case, they won't heat up because of the very low internal resistance. And finally, when we have to assemble all these things into a battery system, and we'll have that performed in Africa. So we've designed the assembly process to be simple enough to not require any advanced tooling or things like that. And we can just have it done all in a workshop in Africa. And and we've successfully demonstrated that is feasible. Okay, and another way we're trying to reduce the cost is let's look at how the battery is actually integrated into a home solar system. So Robert talked about a little bit about this earlier, but you have your solar panel here that charges the battery, and the battery kind of acts as a buffer between the solar panel and the load, allowing the load, which is just a cooker, to be powered when there's no sun shining on the battery. Sun shining on the solar panel. But the problem with hooking all of these things up to the same network here is that when the battery is fully charged, it will shut off its terminals. It will no longer take a charge. And then the solar panel can over voltage the load. Sometimes these solar panels go up to 40 volts, but when they're charging the battery, they'll only be around 20 volts. But the 40 volts that it might jump up to can damage the sensitive electronics in whatever it is that you're trying to power. And therefore, you need this solar controller to moderate the voltages between these three things. But since we're designing a custom system, we can actually absorb the functionality of the solar controller into the BMS, into the battery electronics itself, kind of making a two-terminal battery, like we showed here. And this can save us, sometimes $5 by not having to buy the solar controller. And we can design the electronics of the BMS to be able to withstand the high voltages of the panel. Further, we can integrate it with an MPPT, which basically gives the battery or finds the voltage at which the solar panel produces the maximum amount of power, called a maximum power point tracker. And we can put that between the solar panel and the battery to increase the efficiency of the charging, but that would be optional, an additional cost, but not necessary. Okay, so you can see a picture of our customized battery management system here that goes on top of the lithium-ion cells, and we can just highlight some of the key electronic circuits in here. So basically, everything is handled by a single integrated circuit, a microcontroller, 48-pin package here that controls all the voltage readings and leakings, the current measurements, everything. All the computation is handled by this single chip. And the only thing the analog front end of the triple chip solution has that this doesn't have is kind of this high voltage circuitry that is designed to switch the switches, which are these MOSFETs here. And so that can be integrated with discrete electronic components on the board, which is essentially free. Each one of these components is generally less than a cent. So then put that's basically the only two circuits that really go into this thing, right? It's quite a simple thing, and it allows it to be completely customizable by programming this microcontroller differently. Okay, and we end up with our final product here. So this is kind of a picture of the final product, and you can see these four terminals up top well, 4 screw terminals each, and because there's a positive and negative for the input terminal, positive and negative for the output terminal. You have 2 terminals into the system, and you can see we hook up the solar panel like so, and we load on the outside pins here, and that's clearly displayed on the label, so that when it's assembled into the final system by the technicians in Africa, it's clear how to hook it up. And it's also protected that if you hook it up incorrectly, it won't damage the battery. And we also have an accessible SD card here. So you can put an SD card in this little slot, and it will read voltage. It will report the health of the battery, the currents into and out of the battery, the voltages of each one of the cells, and the temperature of the battery over time. So we can do that recording, greater than 10 recordings per second. The current accuracy of the sense resistor, the current accuracy of the measurements is about 100 milliamps. The voltage accuracy on each one of the cells is about 50 millivolts. You can charge it probably greater at 30 amps. We've been experimenting with that, but at least at 30 amps continuous charge, and discharge it at 30 amps. And you can put as much as 40 volts on the terminals without it damaging the battery. And this is generally larger than any solar panel that you'll find in Africa. And we have, a fuse to protect against overcharge conditions, or shorting the terminals, and for protecting against short circuits, and that will be resettable automatically. It's an electronic fuse, so you can kind of short it as many times as you want. It works well over more temperatures than you'll ever kind of expect to find in the field. And we expect it to last the full 10,000 cycles rated for the LTO cells, because we have these electronics and this protection system that will take care of the cells, keeping them exactly as they want to be within the correct voltage range. And the total capacity for this 5-cell version, or the 12-volt version, is about 110 watt hours. And we also have a 18-volt version, which is 8 cells in series. Okay, I think I'll hand it back over to Robert here to finish things up.
So let me summarize the costs. In this table, we show both the high-low ranges for the different cost components. So the pouch cell can be between, $3.30 per pouch up to $4. You need 5 of them per battery. That's $18 for the cells. The shipping of the battery cells is another $7.50 more or less. There's import taxes when you ship anything. The BMS electronics winds up being about $15. The epoxy is about $7.75. The assembly labor is about $12.50. And if you count for losses and breakage, that's valued at about $11.10. So the total cost of doing a 5-cell battery is about $77, though, depending on how well we manage the costs of the different components, this can range from about $47 up to above $100. And that's roughly the cost we're working with. Maybe if we have higher capacity cells, the marginal cost of extra capacity isn't quite so big. But this corresponds to about 70 cents per watt hour. Next slide. Yeah, so we're going to do a production run of 500 to 1,000 batteries in Malawi over the next coming months. And we're working on demonstrating applying the battery to administer per kilowatt hour eCooking access subsidy. So our customers need some sort of subsidy, and we're trying to come up. We're hoping that if we can measure the kilowatt hours of cooking really well, then we can make the subsidy scheme attractive to financiers. We also are hoping to develop the capacity to, ship out and export a few of the batteries to earn a little foreign income. And I think the battery is so great that other parts of Africa need it. So So I'm going to be sticking with this for a few years and seeing if we can find partnerships in other parts of Africa to produce this battery. So next slide.
Thanks, Robert.
Yeah.
Thank you very much, Robert and Skyler. I'm only interrupting because we're down to sort of the last 10 minutes of our meeting. There's a whole bunch of questions in the chat, and it'd be good to just address some of them. I'll start with one by Stuart at the end, which is about the charge and discharge rate. He notes that the lithium iron phosphate should only really be charged at 1C, and yet your LTOs I didn't realize they could go up to 10C. I knew that they could do 4, 5C. Can you expand on that? Have you tried really whacking up the charge?
Yeah. So I think if we go back to the charge, the data that we have, you'll see that the
slide 4
charge part of the curve is very steep.
Yeah, so then I had a question about it's slide 4 when you get there. Why you're effectively throwing away energy between 10 o'clock and 12 o'clock. Why did you not go for a bigger battery? And this is with a 350.
Our customers can't afford it. So we're sort of stuck. You know, our customers can afford maybe $100 for a battery, and so we're going to have to give them a smaller battery, monitor their behavior, and then see if that specific household would actually get more cooking done with a bigger battery than give them a discount on upgrading the battery. So because the larger batteries will need a larger subsidy, we have to be very targeted with those subsidies, and we're going to focus those on upgrades where the result of the upgrade can be verified from data on the initial first battery.
So I just want to clarify for everybody on the call, Robert and Skyler are working in one of the most difficult situations there almost could be, because they're working with really seasonal farmers. So there's a lot of there's a lot of non-monetary produce flowing around. People can collect wood, so they're not going to be convinced by the modern energy cooking. So, you know, a lot of impetus in Robert's thinking is it's got to be absolutely the minimum in terms of cost. But just picking up on Matt Leach's comment in the chat, you know, that the battery looks amazing and the production process is clear and can imagine it can be performed locally. So that process could be taken elsewhere, and it could sit in situations where a larger battery would be more appropriate. What's this question? Do you think this approach to production can lead to a battery with longer life? Must be risks compared to larger scale factory production. I'm not quite sure why he thinks that. Robert, do you want to try and tackle that?
Yeah, so some of our initial production runs, we had bigger loss rates because people would make mistakes in the assembly. So we've refined and systematized the production process so that our loss rate in assembly, I think, is roughly around the 10% level. So about 10% of mistakes in total of shorting stuff out and burning out the electronics, or not encapsulating things right, or et cetera, et cetera. So that's our number on the first 100 produced, and we'll see what our loss rate is when we try to produce 500 to 1,000.
Yeah, Matt is acknowledging that small scale assembly makes quality control harder. One of the things you skipped over, Skyler, was you're using pouches as opposed to the traditional sort of lithium iron phosphate cells that look like a AA battery. I know they're not a AA battery, but why is titanate sold in pouches? And also, if I can just add to that question, the price of lithium titanate has come down on a learning curve, running slightly above, but very similar to lithium iron phosphate. What are the other uses of lithium titanate that are creating that learning in Chinese factories that is bringing the price down all the time? Because as you said, they have a lower energy density, and so they're not in consumer electronics. That's fine for us, but I'm wondering why the price keeps coming down on them.
Well, half of the lithium titanate technology is traditional chemistry, right? So that's part of it. Like when the traditional lithium ion gets improved upon, it also kind of improves upon the LTO. And for the pouch question, so they also come in cylinders as well. These kind of cylindrical batteries, but it's my understanding that those are slightly more expensive, which is why we've purchased the pouches. Right? They're slightly harder. The cylinder cells are generally easier to deal with and easier to assemble the final battery pack, but the cells themselves are a little bit more expensive. And for the industry applications, like there's some, but they're not very many. I think one of the common ones is in like electric buses that will be recharged by cables overhead. But if they come off the cables, you need the battery to be able to support the bus for some amount of time. So the battery can be small, but it has to have a high power capacity. And there's a few other applications that I think that leverage this kind of really high power output capability of the LTO batteries. Yeah.
Yeah, most of the applications I've seen have been transportation, and the pouch cells are sort of a standard configuration that other battery chemistries are also available in the pouch cells.
Okay. Cool. So very early on, when you were doing your slides, Robert, sorry, Stuart, I'm just reading your comment, and it was about a larger battery. I feel that Robert's probably already answered that because of cost. But yeah, Pete then asks, did they cook more food because they had more energy available because it was sunnier, or did they just use less energy because they chose to cook less food?
So we're finding preliminary data indicates that when they have a battery, they do use a larger fraction of the output of the solar panel. So and when we do the big cooking tests, there are two things that impact the total energy and the amount of food cooked, and that is if the average power rate of the cooker is higher, then people tend to cook more food. And then just how much total power is available from the solar panel for that day. So remember, the batteries we have are basically power regulation batteries. So they're only 1 to 200 watt hours for a cooking system that is going to be doing a total of, say, about a kilowatt hour of cooking during the day. So really the limit on the amount of cooking per day is the total output of the solar panel. And we're finding that with no battery, people cook for every peak watt of solar panel, they do about a watt hour of cooking, right? That's sort of the inefficiency of them only cooking sometimes and not using all the energy of the solar panel. Whereas with the battery, it may get up closer to 2 watt hours of cooking for every watt peak of solar panel.
And there was a comment from Stuart that is it even worth faffing around with MPPT controllers because to try and increase efficiency when the solar panels are just becoming cheaper and cheaper? I know that you've already switched from 350-watt panels to 700-watt panels. Don't you just keep increasing the size of the panel?
Well, I think what we're finding is the MPPT is really important on the cloudiest days. So getting that extra efficiency on a cloudier day is going to determine whether or not you're going to do any cooking at all. And so that's what we've seen. We've seen, but I need to also mention that our least expensive, most popular system has no battery, right? So what happens is, during the course of the day, there's not so much solar power in the morning. So you really want the MPPT to be using every little bit that's coming out of the solar panel at 9 a.m. so that people can start cooking at 9 a.m. and then get a couple dishes done by 1 or 2 in the afternoon.
Okay, thank you very much. We're up against the hour. I learned a lot. I hadn't realized the titanate was on the negative side, the anode side, and I hadn't realized that batteries really degrade because they're literally changing shape all the time, taking in and out electrons. Stuart's just talking about dumping unused power into hot water tank. Robert has got at least another 5 hours worth of explaining the whole project and his engagement with people and everything. This was very much focused on the battery, which I believe is pretty unique in certainly in our experience, and yet has tremendous potential. Stuart at one point puts in the chat that you should give it a lick of paint. I disagree. I've got one on my desk and I like just the epoxy. What Skyler didn't tell you was that they sometimes put in beans just to slightly separate out the pouches as spacers, and that just connects that battery to the whole idea of cooking. I'd like to thank very much Robert and Skyler for doing this webinar, and we will send round the connections. Yeah, some people are clapping. Well done. And please note in the chat, you guys are great, from Paul. And thanks, guys. Great stuff from Stuart. So very good. Thank you, Robert. Thank you, Skyler.
Thank you very much.
Bye.
Nice chatting.
Okay.